Verifying a trig identity is a lot like simplifying a trig expression in that we use trig formulas and some basic algebra in order to simplify. However, in verifying a trig identity, we run with the added benefit that we have a goal. We know what we're going to end up with. In this particular question, let's say part C here, right here, I noticed that there's a lot of parts of this that look a lot like double angle formulas, specifically cosine double angle. So I have the formulas cosine of 2 theta is equal to both cosine squared theta minus sine squared theta, and it's equal to 1 minus 2 sine squared theta. We can make both of these substitutions on just the left side of this equation in order to turn them into cosine 2 theta. So on the left side, I notice we have 1 minus 2 sine squared theta inside this square right here. That we can just turn into cosine 2 theta. The denominator is not quite so simple. We have to the power of 4. However, we have 2 squares being subtracted. They're part of the power of 4, but it's really just a square of a square. And thus, it's a difference of squares, which we can factor accordingly. That is cosine theta, cosine squared theta, minus sine squared theta. And, just to give myself a little more room here, cosine squared theta plus sine squared theta. And it's equal to this. Now, this denominator, you may notice, has cosine squared theta plus sine squared theta, which is just 1, and cosine squared theta minus sine squared theta, which is just cosine of 2 theta. So we end up with cosine squared 2 theta, to bring this square into the cosine, divided by just cosine 2 theta, which is just equal to cosine of 2 theta. And now we're going to look at the right side of the equation and notice that it's another formula for the cosine of 2 theta. That is, it's equal to cosine squared theta minus 1. And thus, we can take this trig function right here and just turn it into our answer, 2 cosine squared theta minus 1.